started. Today I thought I'd go over Module 6, which, you guessed it, is revisiting our good friend um, cross-validation and k-fold. So, jumping straight in, by the end of this the module, you'll be able to apply cross-learning methods for validation in your modeling process. You'll have the ability to utilize model validation, explain cross-learning method, and apply the cross-learning method into a real data set. So, straight in, what is model validation? So the basic idea here is what we've talked about numerous times. You hold out a portion of your data, and in fact, you split it into three pieces. One is the training set. That one's pretty straightforward. It's what we use to train with. But how do you know how good it is, right? And that's where there's two additional sets that are utilized. One is the test set. That is very common. You probably saw that in earlier courses, and that's where you basically reserving it to see how well you did at the very end. That's something that the model does not see until you're done, and it ensures a certain degree of accuracy of the results. The other one has different names. Sometimes it's called a holdout set, which is what it's called here. Also, it's called potentially a validation set. The distinction is that it's used during training. So in the case of a neural network sort of approach, as you're training, you reach the end of an epoch. So you've basically taken all of the data, ran it through your neural network, and adjusted weights and whatnot. And so then you want to see how good it is kind of at that moment in time. And rather than using your test set, which could invalidate your results, instead you use this holdout set or this validation set, and that basically gives you the ability to determine the accuracy on your validation data, and then the idea is that once you're finished with that, so that you feel that your validation data results are good enough, then you do the final test, you stop training, and you run it against the test set. One of the key things that you typically do is save checkpoints at the end of each epoch, and the idea being that you could then resume from a given epoch. Sometimes things happen. Sometimes the computer reboots. Sometimes the cluster goes down, and you need to basically pick back up. So if you've got something that takes 3 days to train, you don't want to start back over if something happens on day 2.5, right? And that's one of the things we do is typically save as a checkpoint. So again, what is this whole validation thing? And it's what we said. You do the test train split. That's where you basically take your data, you split it into, at the first level, two groups, the test set and the training set. That test set you could actually then think of being split into two more groups, which is your holdout set and your true test set. And the ratio really depends on the amount of data you've got. So if you don't have a lot of data, you may end up having to use a good bit of it to do your testing with. So it reduces the amount of data you have to train with. You also have the potential that because of the limited amount of data, that it may bias it, and we'll talk about that, the k-fold approach, to address that. And so there's a few rules of thumbs, but the general approach that you use and you've been using is to use the train test split function in the scikit-learn library, and it is a good and common way of doing this. So I mentioned k-fold, and it's one of those things that on the surface may sound a little more complicated than it really is, but the reality is it's pretty straightforward. What you basically do is take your data, split it into k buckets, k being a number from 1 to something or 2 to something, because it'd kind of be stupid to do 1 k-fold, but somewhere in the neighborhood of, say, 5 or 10. And what you do is you split it into different buckets, and so that during a given iteration, you're using a different piece of your data. So you take the first bucket, you hold it out for your test set on the first iteration, and you use the remaining 4 or 5 buckets, whatever they are, as your training set. Then on the second iteration, you move it over one, right? So you take that second bucket instead and use everything else for your training, and the second one becomes your test set. And then on the third iteration, you move it over to the third bucket is your test set, and everything else is your training, and so on. And what that ends up letting you do is basically make the best of limited amounts of data. And so it's not violating the rule of letting the test and training data be seen, most likely, although you still might want to consider doing a variation of this, which is you take your test, you do your original true test set, hold it out, and then the remainder you do this approach and basically use that, what is the holdout in this case, for each of those iterations as your validation set. That would be perhaps a little better approach. So moving in and talking a little more about K-fold. And again, cross-validation approach, and it does pretty good actually, but this is kind of a visual way of seeing it. On the first one, you're taking fold 1. On the second one, you're taking fold 2. The third one, fold 3. Those are your test sets, and everything else is training. So it can give you pretty good results, and it is such a common thing that many of your tools and your libraries kind of have it just built in, because it is something that you want to do. If you take a look at things like Orange, the graphical data science environment, whenever you do test train sort of score on your of your data, it has that kind of there by default, and in fact it's naturally selected to be turned on to a certain number of K. I think 4 or 5 is the default value. So it is such a common thing that we always do it. So cross-learning into real data sets, and this is where you basically have to make sure that your neural network is not seeing data before you really want it to, because what ends up happening if you're not careful, and the biggest thing you're trying to avoid with this is this whole overfitting or underfitting of your data. So you can think of it as, if you overtrain on your data, then you will do really, really good on it, right? Because you're basically matching that curve or whatever shape it is perfectly. But at the point you show it something new, it's going to do very poorly because it's never seen anything like it, and it doesn't know what to do, and it doesn't generalize well. This is what it comes down to. One of the key things with any of these approaches, and this is something that there's actually a significant shift in the approaches of a lot of AI and machine learning individuals these days, which is focus on your data is a key thing versus focusing on the algorithms. Rather than getting a whole bunch of data that's so-so, get a smaller set of data that is really clean is the idea. And so that means you may end up needing to do, and clean meaning that it's accurately labeled, not necessarily clean in the sense of free of noise. And in fact, if you're wanting to train something that may be used, say it's an audio recognition or an image recognition that's going to be used in a situation where it's likely to encounter noise, you would likely want to train on noisy data in the sense of audio noise or visual noise. But you do want accurate and pristine coding of your data sets, so that if you say that it is something, it is always that thing, and there's no misinformation in your data. So that it takes a lot of time to label your data. So it sounds like you just joined. Hey, John. So I'll go ahead and back up. Not that big of a deal. I went ahead and moved up to module 6. I'll go ahead and stop before I go into it. Oh, good. Thank you for joining. So yeah, that would have been a pretty boring one to watch. So I do need to redo it then. So no, it's good. It's good because yeah. Would have been trying to read my lips, right? So I went ahead and moved up to module 6, cross-validation. It's the same thing we talk about a lot, right? But I'll throw in some color commentary, so hopefully it'll be something new. But before I do that, did you have any questions or anything going on?
A comment and a question.
Okay.
First of all, I absolutely else's training, and download all those weights, and then just reapply it to your knee.
Yep.
And the light finally clicked as I was doing the paper on the convolution process.
Yeah.
The book that I had from Springer, um, everything I'm reading makes a lot more sense now. So that was super cool.
Good. Good. One of the things that I'll probably be some of the material in this course, and it's not just this course. Um, it's almost like it missed something that it should have had, right? So I'll say it that way. So what when I read this, and it's talking about cross validation on is kind of the thing, but they also threw in model validation and then cross learning. Cross learning, I think the original intent probably of the person who wrote the course description was transfer learning. I think that's what, yeah.
Okay, that makes sense.
And so what I'll do is we'll talk about validation and holdout and all that good stuff. But then I'm planning, is assuming I can pull it together to talk in depth about transfer learning next, because I think that's necessary, and that's probably part of what you saw with. I don't think you actually adjusted the weights much on the one you used. It was just pre-trained, right? So
Yeah, the DV16 were
right,
pre-trained to even differentiate between types of gravity pads.
right,
What we did was we stripped off the back layer of it and made it a sigmoid function so that it's just a dog knockout basically or cat,
right, yeah.
which is super cool.
S-
Just exploring other things.
So what I was looking at, and I want to, I'll find it later, is the idea of transfer learning is you take that sort of approach, but you take it a step further. So the idea of the whole concept is that sometimes you can take it, you train it on one domain even, and be able to take it out of that domain and do some transfer learning against it and actually use it in something totally different. Or better yet, you may want to refine the domain. So whenever you go and use something like these, I don't know, cognitive services in Azure where it'll do speech recognition for you or image recognition and so on, you have the ability to take that existing model and make it more adaptive to your domain. So imagine you're in the medical field, you would train it on a whole bunch of medical terms, right? And so rather than having to start from scratch with a random starting point and train it all on all the data that was existed and then add your own data, you can basically do some transfer learning on the end, and you're kind of adjusting those weights on that last layer is what it kind of comes down to. But it's incredibly powerful because it allows you, first of all, to see that reuse of somebody else's model. But then you can make it really accurate in your domain. So pretty interesting stuff. So I'll probably get that in next week. I've got a little bit of work to do first, but I'll go ahead and talk about this because it's relevant, and especially there's some other things that I'll talk about too that aren't necessarily explicitly mentioned, right? So the basic idea here is like we've talked in the past. You have your data. You split it into 3 chunks, basically. 2 of those chunks are essentially for testing purposes, and the third is for training. And the ratio of that depends upon the amount of data you have and the distribution of the data and lots of other stuff, right? So you may do something where it's 70, 15, 15. You may do the 98, 1 and 1 if it's a really big data set, because that might be enough. Or if it's a really evenly distributed data set. But the basic idea is to get the proper level of fit. You don't want to overfit, you don't want to underfit. So the only way you can do that is to have some data that you're testing with along the way. Those two sets that you use, one is the validation set and one is the true test set. Validation you basically use at the end of each epoch. So you do all your training, run all your data through, and At the end of that, you see, well, how good did it do right now? So you use some data, and that gives you a sense of where it's at. You'll also probably want to create a checkpoint so that if something bad happens, you can resume from that point, right? You wouldn't necessarily do that at the first one, but I've been on some projects where it took days to train. And whenever you're doing that, you save your checkpoints because machines get sick and reboot, or somebody somebody turns it off. There's lots of bad things that can happen, right? So that's kind of the general process. You train it, you validate it, and then whenever you do good enough on your validation, or you start seeing that you're getting too much loss in the whole process, you stop, and then you take it and one time you test your test set against that, right, or whatever, but you don't test it and say, oh, it's not good enough, and so let's run it back through again, or it's not. That's kind of the whole scientific method sort of approach, right? You're breaking the rules. And this is basically the same sort of stuff. The basic idea is to use train test split. It's your friend. There's a reason it's in scikit-learn, and almost every example you see uses it. And this is such a common thing, which if you go into Orange and you use its test evaluate sort of function, where you can basically hook up a data to this control and then give it a series of classifiers, by default it's doing the split, and it's not only doing that, it's doing this k-fold approach as well, right? And you probably know k-fold. It's just you split it into k buckets, you hold out one, do the others, and switch it out, right? Yeah.
They explain it so well in there, the examples I went through all those. I just really think it makes a lot of sense, because I've discovered, like in the metals business, I discovered that there were some really weird rules that tariffs were imposed that things just wasn't going
Mm-hmm. Yeah.
one of the holdout sets really exposed that.
Yeah.
So we actually wound up reading that.
Right, and there's also, I guess from a purist perspective, I would probably do this from a training a neural network approach for the validation set. I would probably still want to hold out my true holdout set so that it never saw it. That's just, that's probably overkill, but yeah, because I could see that there's some anomaly that you train around because you see pieces of it over time, right? So anyway, that's my take, but not necessarily. It's more just the especially some of the things I've done. You don't want the model to ever see something just so that you can get a true sense of how good it's doing, right? This is basically the same sort of visualization, just explaining it in a slightly different way. Pretty cool approach, pretty simple to understand, but very powerful. And this is basically the same sort of approach to where you should always be testing on unseen data. I mean, and it's saying it again over and over, right? But that's the same basic thing. And so the key piece here that I don't think has necessarily been accented in this course as much as it should is your training data has to be machine learning quality data. And I'm sure you've seen this in your work as well. I've worked on one project where the client thought their data was good. It was not. It was maybe 80% good, and that's not good enough, because that means that you're probably going to approach 80%, but you won't ever get there, right? And if your goal is 95%, you're not going to make it, right? So, and actually, there's a shift in the whole approach in the industry towards not necessarily huge data sets, but pristine data sets that are rather than spending all your time like trying to come up with some clever algorithm and all that stuff, it's get your data right, get it clean, get it straightforward, and then once you've done that, then start worrying about how good is it. And that doesn't necessarily mean, like if you're doing speech recognition, that doesn't mean you want studio quality necessarily audio. You want it to be representative of the audio that it's going to see for real. So if you're going to be working on a 50-year-old telephonic system, your audio should come from a 50-year-old telephonic system. And you may actually introduce noise yourself. Take something and just as we do with images where you rotate them or shrink them or move them around to create more data, you may actually want to introduce some noise as well.
That's brilliant. Yeah. That image augmentation,
Yeah. But I was actually on an aside looking at how to determine how similar images are. And I'm actually going to do some work on it. More from I'm trying to find submissions that are images, say an ER diagram, that are just too close to each other. So anyway, that's one of the things I've been looking at as well. So the other piece that I don't think we've really talked too much about in here is feature engineering. Maybe that's touched on earlier, but you oftentimes have to do that, especially when you're doing machine learning. So you have to take your primitives and construct something else. It may be taking the date time and turning it into the day of the week. It may be all that kind of stuff. And I don't know that they've really ran that in, and that's kind of important. But anyway, I'll probably talk some about that stuff as well, featureization and all the fancy words. But anyway, so jumping into the demo of doing K-fold. So when you may find something interesting that's not necessarily about doing this, but so I've started doing reading from my GitHub account. So that's a URL to a CSV that's in GitHub. So that way I don't even have to worry about where my files are. And so it takes a little bit longer because you got to go get it, right? But once you've got it, it's not too bad. So basically our good friend Iris, again, and then separate the data into the input and essentially what we're trying to predict. Print out the columns. Not the first time you've seen this, I'm sure. Use a one-hot encoder on the input. Did they talk about that in any of your other courses, by the way?
they called it flags, setting flags.
Yeah.
Same type thing.
Yeah.
It's a binary, it is this or it is not this, and then you have to enter for each of the things. So it's literally one hot to read and out.
Well, in classification, what they do is a series of columns that do it, right? What the one-hot encoder does is literally a vector with essentially one of the bits on and off, right? So, and you could actually go even more to where it's not that's a list, right? It could even be tighter than that, depending upon how many features you're manipulating. Anyway, so K-fold, doing 5 folds, and we're doing shuffle as well. And so shuffle the things around, and we want 5 different chunks, and then basically create the model. Really complicated one here, right? It's it looks like what, 2 layers basically. But again, I do like this sort of representation. I don't know if you've looked at some of the other neural network code out there. It's this approach is so much more elegant. Anyway, taking.
Is this, do you have the link for this
Yeah. Yeah, that's right.
demo?
Oh, no, I stole it. I there we go. I'll put it in here. Actually, was a pretty good one. Um, so that's yeah, a pretty good one. So that's I'm getting pretty picky about where I steal from. Anyway, moving on. When it's not stealing if you give them credit, right? So I try to make sure I put it up in the top.
Science.
Yeah. Yeah.
Reproducing research.
So here we're basically turning it into what, an array of ints. Let's do. Oh, that may cause me grief. No, oh, okay, it actually worked. I was afraid because it's assigning it back to itself. I was afraid it's going to give me grief. So here we're basically going to run for 50 epochs. It's, if I remember right, this is really fast. And we're going to go through each one of the splits, getting the model, fitting the model. And this is actually kind of nice because you can actually see the application of the fold. A lot of times it's even abstracted away where you don't necessarily even see it. So we'll go ahead and queue it up, and if I remember right, it's pretty fast. It's not too bad.
Yeah, that one.
Yeah, it's not that many things to. So yep, I think we're done. Or yeah, we are. We're done. So then plotting it, and you can see the cross-validation score and the train score pretty decent. It's a pretty nice plot too. And then talks a bit about the improving. So that's basically it in a nutshell, right? Now, what I want to talk about later, I'm not quite ready yet because I don't have the data down, is this one, which is a dog breed classifier. And part of the reason is it's going off that Inception v3 model and then doing transfer learning on top of it, right? So should be pretty interesting. So that's what I want to look at next. And there's a book out there that is like hands-on transfer learning, something like that. Transfer learning with Python. Hands-on transfer learning with Python. Yeah.
That's fascinating.
Yeah. Yeah, because that's it's one of the powers of this sort of thing. So let's see. What I want to.
Let's do all that work creating something and you just like take it away.
So the other thing I wanted to show, I don't think have I shown you AutoML yet? I don't think I have. So what I'm doing right now is kicking off, starting up a cluster. This is Databricks. What I did previously to get ready is I took and dropped a CSV onto this little box that says drop files here, basically. It walks you through a wizard when you do that basically it loads it into a place inside of its file system and then creates what looks like a table on top of it. And the reason to do that is once you have that, then you can go through and you basically treat it like a regular table. Under the cover, it's Hive, and this is Spark running underneath of it, hitting that Hive table basically. Doesn't matter too much. You'll talk about it more in the big data class. But the part that's cool is the things that the company Databricks is doing with that technology. Generally, when you do AutoML, what it does is they do what you would do as a machine learning person. They fiddle with all the various types of models, all the hyperparameters on each one of those models until they get something that's good enough. And good enough is defined by you when you're setting up the experiment. You say, I care about F1, right? That's the value that we want to score them by. And then it churns on it for a while. Either you reach some level of accuracy or you do a certain number of iterations. Or you run for a certain amount of time, right? So it's bounded so that it doesn't just churn forever. And then traditional AutoML basically then gives you essentially a serialized model that you can expose through an endpoint like a REST API or something, so that you can use it, right? So it's a way of doing it to where you can get to production really quickly.
So what
Well, it's a way that you probably used them. It's the formatting is it's just in the URL has something that tells it what to do is what it comes down to. S- Uh,
It's the your get and post HTTP
right.
database packed. Okay.
Yeah. When all it is REST is basically it's generally stateless. And you'll say, okay, you're going to allen.com, and then you have slash home slash maybe get info or something or index, right? And it'll return back to the caller essentially a JSON string that is then rendered typically with some sort of JavaScript thing on the client side. So the basic pattern you do with those kind of applications is pretty much that. You have a lot of times a single page web page, right, that makes a HTTP GET to with enough information in the URL that it can tell a server what to do. And yeah, and generally it's about either getting information or sending information. Although usually if you send it, you're doing it with a post because it's bigger, right? But it's really not. I'm sure you've used one and just didn't probably know you had, right?
Yeah, I think the part that you added that, because to me it's always sounded like the old network programming I used to do.
Yeah.
Get and post, gets all up in the URL and post is embedded in the body. And I think that the new element is the JSON, the treatment of JSON on the client side. That's probably
Well,
part of what makes up REST and makes it something different than what we were doing.
well, if you look at, actually, you can see it here. This is under the covers. It's talking to the slash clusters is saying get back the list of the clusters. So it's returning that back. This is the organization unit, and I'm in the settings section, and I want to see the clusters, right? So it's basically saying where I'm at inside of here, but that's also what's being sent to it. So if I won't let me. So there we went into this particular cluster, which is this bit here, and we're saying give me back the configuration information. So underneath the covers, this thing is doing it. It looks like it's moving around. It may or may not actually be moving around, right? And that's where you can actually see the JSON that's coming back and forth inside of Databricks. They're pretty clever that way of letting you see this is what's being returned. So I've got 3 workers. I've got a name on it. So that's, and it probably even tells me it's state somewhere. Not yet. But I think we're up. Good. So, whenever I uploaded the file, it created inside of this data, what looks like a database. It's not really, a file, and they have the concept of, they call it a database. It's really kind of like a schema, if you were from a purist perspective. And I uploaded this file called Iris Data, and you can actually see what the data looks like. But it's not really very advanced. This is a CSV that's sitting on in a folder that it's reading and applying the schema that it inferred during the upload on it so that it kind of can know what to do. But
So timetable on the fly when you route the data and infer the data types.
basically, yeah, there's a simple UI to do it, but yeah, pretty much, yeah. You can overwrite it if you want, and you can also create a notebook that creates the table as well. And then they take that a step further with lots of other stuff, but that's basically all you kind of have to know to get going. So they have this persona. They've started switching it over now. So you've got this AutoML persona. So you can go in and say, I want to use AutoML. I've got to pick a cluster. The cluster has to be running a machine learning runtime. All that means is it's preloaded with all the cool stuff you need. So it's got scikit-learn already installed. It probably has PyTorch and TensorFlow and all the common stuff, so you don't have to set them up. Then I say that I'm doing a classification problem, not regression. It looks like they're working on forecasting. It's available in a certain version. It looks like 10 of the runtime. Then you pick the data that you're interested in. So I'm going to pick this Iris data, and select it. And then it says, well, what am I trying to predict? And it's the class, right? Uh, based upon that. And you can give it an experiment name. And then you can say, well, I care about F1 or something else. And then I can say run for 30 or 60 minutes or 200 trials. We'll take that down to a good bit smaller. And then you say start. And so when it does that, it's going out and going to literally run through lots of different combinations. And I'll do the cooking show bit here now, right, where I switch over. It's one that we don't have to wait. Really cool, sort of cool. They give you an exploration notebook after a certain amount of time. So it turns for a little bit and then it pops that up. So you can open that up. And it's kind of cool, but really what they're doing is running a profile report on pandas, right? So it gives you back all of the variables, the all of that stuff.
I always forget about that. I think that's such a neat thing.
And then you can start looking to see, well, what's the relationship between the various things. And I mean, it's not gonna put like Tableau out of business, but it's pretty cool, right?
It's great for what it's doing.
Yeah. No, the interesting part here, though, they're kind of breaking their own rules. Pandas isn't really a Spark thing, so it's a Python thing, right? And it doesn't run on a cluster, which means basically if it's running on a single one of the nodes, and is it's one of those things that if I were interviewing somebody for a job doing Spark and Databricks and they said, oh yeah, I like to use pandas a lot, that's minus 10 points or at least, right? So it's not good. But I can see why, because if you think about it, a big data problem of doing this is hard. Of how do you profile data if your data is in petabytes? You've got to do some sampling or something, and it's hard. But anyway, they kind of give you this, and then they do the head and the tail, and look for some duplicates, and the most frequently occurring. So pretty cool stuff. Let's see. Well, it's did I go back? Or did we pop a new window? I think we popped a new window. Yeah, that's what we did. So this is also showing the results, and it gives you this nice little link here at the very beginning of view the notebook for the best model. So based upon F1, I can, I'll go ahead and open up a new tab because I don't want it to navigate for me. It actually gives you the code it generated to do the model. So it uses MLflow, which it's a cool technology into itself, but it's basically how they're doing all of this, how they're scoring stuff. That's actually MLflow. They didn't create all this. These are the model that's being used, the parameters that were being used, and so on. It's kind of like a little repository that keeps the values, and then you can actually deploy from there if you were so inclined. But what's really cool, though, is it said here, okay, we're setting the experiment to be, it's on Databricks, AutoML, Iris. Then we go and set up the MLflow client, which is just kind of housekeeping. And then basically, if there's any pre-processing, figures out the numerical columns, does any kind of transforms that need to be done, standardize scalar, and then it transforms it to a standard. Here's our good friend test train split, and does looks like a little more stuff in here. It does a stratify and a random state so that it's probably predictable. But they didn't use 42, so they lost some points there. But anyway, this typical sort of thing of splitting it up into your X and Y train and test, then run through. Looks like the logistic regression was the best on that. They tell you a bit about the model they're using, kind of cool. And then show you the pipeline that's going to be used as well. So it's really cool and also really easy to read, right? Because you can see the model is a pipeline, and this is actually a Spark ML thing, so it's a ML Lib sort of implementation. So cool stuff. Also, though, leveraging scikit-learn as well. Setting up the pipeline, doing some auto logging of various values. Then they do the training, figure out what the accuracy. It's kind of hard to beat it. One, and and then do some feature importance. Figure out what features are important. And then if it's enabled, they actually will plot it out for you. Looks like we're doing some inference. And they actually give you here, if you really wanted to load it, here's the code to load it. And you could be running this in a production environment really quickly. So, and the part of this seeing the code is what makes this cool, right? Because all the rest of it you can do with pretty much all the AutoML stuff. But they use what they're calling a glass box approach, which it is glass box. But more importantly, it's well-written code. And if you think about what they're doing under the covers, it's probably not all that hard to do this bit, because they were probably generating all the stuff anyway to do it. And then they thought, well, why don't we just save that, right? and so
Cool. When it comes to interpretability and adoption, glass box is so much better than white box.
Oh yeah. Well, and you trust me, right? It's good, right? But no, it's magic is what it is. Inside of this, there's just something that works. Don't you worry your pretty head about what I'm doing in here, right? I mean, that's like, yeah. Anyway, so I'll go ahead and shift back. Talk about deliverable 6. You guessed it. You get to apply cross-learning for validation of the process. And you get to pick, right, what you want to do is, so explain and utilize the model validation, an example of your own choosing, so go pick something. Explain what cross-learning is, and I'm pretty sure what they're meaning there is this holdout approach with model validation, and then do it using test train split, sort of thing, and then write up a report. So pretty straightforward, and some code if it's appropriate. Yeah, the learning there, I think we need to talk about transfer learning, but that's not what they're asking here for. And more because I think transfer learning is some cool stuff, right? So, and you might, yeah, and you might actually need it. So, and as always, shoot for the mastery, which you do. I think it's just pretty straightforward. And then deliverable 7, you kind of tie it all together. So you're going to explain all of neural networks. You're going to design one using basically training data. And that's where observational data, that seems stilted to me. I mean, that's what it is, but it's historic labeled data is what we think of it as. Anyway, you're going to do some classification. You're going to do an SVM and a little genetic programming, and then cross-learning or cross-validation. Big Heads International or whatever. Anyway, your instructions, so explain neural networks, basically. I'm fine if you reuse some of the stuff you've previously done. Explain backprop, gradient descent, typical results of each step. Sounds awfully familiar, doesn't it? How do CNNs work? This is the one that was don't freak out on me, because it talks about provide robot with high eyesight and the ability to detect and recognize things. I think this is the one that also talked about using a really big data set or something. Don't worry about it. Just pretty much follow these instructions. Talk about the things that we've talked about so far in the course: SVM, what is a kernel, regulation, gamma, and margin, genetic algorithms and programs, Python to use that. So again, it's just basically pulling together the stuff you've done in the previous assignments. And then appropriate performance function, sounds awfully familiar. And then model validation and cross-learning. So pretty much frankly, I don't see much here that's new, right? It looks like it's almost a pull together everything you've done, harvest and, uh, you know, wordsmith it a little bit. It's probably that. Yeah, it's. I think this is the first one I've seen that was so blatantly this, right? Normally, it's like,
It's pretty much a review.
yeah, I mean, normally they at least say on a different data set, right, or something like it's basically the same stuff but switch data sets. Here, there's not doesn't seem to be that. So, yep, should be a pretty easy one for you.
Yeah, I think it'll be fun to do. The support vector machine, I'm on that one now, and I coded literally like 10 minutes. It's using the iris data set. It's not very complex, but I guess that's okay.
Yeah,
I like the low dimensionality because it's easier to chart.
yeah,
With the explanation in there.
right,
To demonstrate that I know what effectively. I'm gonna wrap that one up here in the next day or two, hopefully. I'm eager to get to the point about the because that's new and weird. I got a book called Deep Learning Deep Through Examples.
yeah,
I wanted to spend some time on that one just to get my head around what's actually going on. But the curve approximation example that you showed
yeah,
before has kind of stuck with me. And one of the things that I thought about just randomly as I was driving was I think that one of the reasons those things lost popularity is because computing power has increased exponentially since
yeah,
that became a thing.
yeah, yeah,
Now you can almost randomly, achieve a better result
yeah.
than you could back then. The need for approximation is probably less common than it used to be.
Well, and the whole concepts of big data and distributed processing, I mean, you can literally solve for n and not have to sample and not have to approximate. So given that, then yeah, why would I do that? I can get the actual value. Now, there's probably situations where it's still relevant, but it's nowhere near the popularity that it once was. I mean, it's not quite a footnote, but it's there's not a lot of it going on, right? Most things now are support vector machines. They're pretty popular. The various types of neural networks, and even rule systems kind of lost popularity as well. They're not nearly as. I think they'll come back. I think they'll have to come back because I think you'll need them to control the various sub models so that they don't break the rules, literally. So I think eventually they'll come back, but it's a lot less than it once was. Everything's connectionist right now. But I think when we start talking about things like autonomous driving, rules like stay in your lane, or do the speed limit. They're going to be there, right? Governing as a
Sure.
control.
Sure.
Yeah. But
That's
anyway,
a good observation. Makes total sense.
yeah. I think there'll be, I
France of the optimization, right?
yeah, and I think there may be a point where, by default, your car won't go over the speed limit. I think that'll be coming at some point. And then you would have to go in like you do with your drone, right? If you go buy a drone, it won't go over like 400 foot above your elevation by default. You can turn it off with lots of warnings. By the way, you're violating FAA rules and blah blah blah. But I think we'll start seeing that with our cars at some point.
All
So
right. Wouldn't surprise me at all.
yeah. All right. Well, thanks for joining. Always appreciate
Yeah,
it.
you bet.
And if you have any questions with anything, let me know. I'll try to get something together for transfer learning because I think that's some cool stuff. Um,
That's pretty interesting. Yeah. I was blown away. I love that stuff.
yep.
I'll pound on this support vector machine some more, and we'll see you Thursday.
All right. Sounds good.
All
And
right.
have a good evening and talk to you later.
Have a great night.
All right. Goodbye.